Your database optimizer predicts milliseconds, but the real execution takes minutes because of stale statistics and physical disk latency. The explain analyze command executes the query and returns the actual timing, row counts, and memory usage for every node in the plan tree. Always set track internal input-output timing to on to differentiate between high central processing unit usage and slow storage subsystem response times. Actual time shows the startup and total completion time in milliseconds. Use this to find exactly where the execution pipeline stalls first. Massive differences between planned rows and actual rows indicate that the optimizer lacks fresh statistics or has misunderstood data correlations. Sequential scans read every page from the disk. This is efficient for small tables, but creates massive bottlenecks when scanning millions of irrelevant records. Index scans traverse the B tree structure to find specific pointers. Analyze shows the number of index pages visited versus the total records retrieved. Index-only scans avoid the heap entirely if the visibility map confirms pages are clean. Check for heap fetches in the analyze output.
Bitmap scans identify relevant pages first and then read them in physical order. This reduces random input-output overhead compared to standard index scans. Nested loops iterate through the inner relation for every row in the outer relation. High loops counts and explain analyze signal quadratic complexity risks. Hash joins build a lookup table in memory. If the hash table exceeds the work memory setting, it spills to disk, killing performance. Merge joins require sorted inputs. If the analyze output shows high sort times before the join, consider adding indexes to provide pre-sorted data. When sorting cannot fit in memory, Postgres uses an external merge sort on disk. This is often 10 times slower than an in-memory quicksort. The buffers line shows shared hits versus shared reads. A high read count means the query is waiting for data to be loaded from storage. Look for the rows removed by filter metric. If a scan reads a million rows but only keeps 10, your index is not selective enough. Parallel plans launch background workers. Analyze shows if one worker is doing all the work while others remain idle, indicating poor data distribution.
Materialized nodes store intermediate results to be read multiple times. This uses memory and can lead to unexpected execution time spikes in complex joins. In older versions, common table expressions acted as optimization fences. Modern databases can fold them, but materialization can still be forced with the materialized keyword. Just-in-time compilation speeds up expression evaluation, but adds a startup overhead. Check the JIT section to see if generation and optimization took too long. Volatile functions are executed for every row, preventing the optimizer from caching results. Use stable or immutable categories to allow for better plan optimization. Analyze reveals the overhead of triggers during inserts or updates. These costs are often invisible in standard logs, but appear as separate execution nodes here. Partition pruning allows the database to skip entire tables. Analyze confirms if the planner actually excluded partitions or if it scanned the entire inheritance hierarchy. High offset values force the database to scan and discard thousands of rows. Explain analyze shows the wasted time increases linearly with the offset size. Postgres can use memoized nodes to cache results of parameterized subqueries. This drastically reduces execution time when the same input values repeat frequently.
Even select queries can report dirty buffers. This happens when a query must clear modified pages from the cache to make room for its own data. The planner uses histograms to estimate selectivity. If data is skewed, the estimates fail. Use analyze to verify the actual distribution versus the model. Index scans are most effective when the leading column of a multi-column index is in the filter. Analyze shows if you are getting an index skip scan. Filtering on a function result ignores standard indexes. Use explain analyze to see if an expression index is needed to speed up the transformed column lookup. Low correlation means physical row order does not match index order. This causes high random input-output. High correlation allows for much faster sequential reads. Subplans can be executed once per parent row. If the parent has a million rows, the subplan is a hidden loop that kills query throughput. While explain analyze focuses on execution, large gaps in timing between nodes can indicate waiting for row-level or table-level locks from other transactions.
Hash aggregates use memory to group data instantly. Group aggregates require sorted input but use less memory.
Analyze shows which strategy the planner chose. Window functions like row number or rank require their own sort and materialize steps. Monitor the analyze output for high overhead in these specific nodes. Advanced clans use Bloom filters to drop irrelevant rows before they even hit a join. Analyze confirms if the filter effectively reduced the inner relation size. Prepared statements might use a generic plan that ignores specific parameter values. Use Analyze with different inputs to see if the plan changes for skewed data. Querying remote tables via foreign data wrappers adds network latency. Analyze reveals the remote fetch time, showing if the bottleneck is the network or the remote database. Running the Analyze command separately updates the internal statistics used by the planner. This often fixes row estimation errors without changing a single line of code. Incremental sorts take advantage of data that is already partially sorted by an index. This avoids a full sort of the entire dataset, saving massive time.
Identify the slowest node, change the index or settings, and run Explain Analyze again. Optimization is a cycle of measurement and refinement, not a single guess. Explain Analyze actually runs the query. Be extremely careful with updates or deletes. Wrap them in a transaction that you roll back to prevent permanent changes. The top node shows the total query cost and time. Indented nodes are children that feed data to their parents. Always start your analysis from the most expensive child. If you see disk spills in sorts or joins, increase the work memory for that specific session. This allows the operation to complete entirely in the fast memory space. Parallelism is not free. Analyze shows the time spent launching workers. For short queries, the cost of coordination might be higher than a simple single-threaded scan. Stop guessing why your queries are slow. Use Explain Analyze to turn database performance from a mystery into a precise engineering discipline based on actual execution data.